Physics students, hello. Pardon my cold. Got a cold. We're going to talk about some fundamentals of calculus operations in the context of physics. You know, that's the reason there's calculus, don't you? For physics. So here is a standard kinematics situation. Here's an object's velocity. It varies with time via the following expression. So we have a time-dependent velocity, and we're going to find the instant at which this function reaches what's called an extreme. We're going to determine the magnitude of that extreme and figure out if it's a minimum or a maximum value. So what we mean by this is, now I'm sort of going to, I'm almost answer the last part first. I'm going to make a qualitative sketch of v as a function of t. Now, there are other ways to do this. You could use one of your fancy graphing calculators, but here's what I know. I know that let's see. Look, like when t is 0, this function has value 0, right? Plug in 0, you get 0. It happens to be that. Now, when t's are really small, if you cube a really small number, it gets really, really small, all right? But the number itself, relative to the size of its cube, is bigger than that. So that means that I'm going to say for small t's, 2t, that magnitude, is bigger than 4t cubed for, quote, small t's. So what that means is this term is what I would call the dominant term when t's are small. But later, the opposite's true. For larger t's, when you cube a large number, quote unquote large, what does that mean? But, bear with me. When you cube that large number, it gets really, really large. So when t's get, quote, big, then that 4t cubed number becomes big. Much bigger, perhaps, yes, much bigger than t. So what this looks like, well, this is a linear function, right? T raised to the first linear. So initially this looks like a downward, see I'm down here in the graph. This looks like a downward linear function, but then this function starts to go up, quote up, in a cubic way. So the function looks something like that. That happens to kind of look like a parabola, right? It's not supposed to, but that's generally what the function looks like. Okay, and so this place right here, we know this is the extreme, the extreme, and this is a minimum. It's what we call a local minimum. Minimum meaning v has reached a, not smallest magnitude, but most negative value. Okay? So we want to find when this is, what is this instant? We want to find capital T, and then we want to find that velocity, we want to find that velocity v at time t. We want to find its magnitude. Okay, so what we have to be able to do is say, look at this great graph we've drawn. How can we use this graph to figure out what we need to figure out? Well, look what happens when v gets to an extreme. What happens is right now, the slope of this tangent is 0. Okay, when I just said slope of tangent, well, what that means is, that means that the slope of this tangent of a VT graph is a instantaneous. Well, slope of tangent of VT is the instantaneous rate of change of the velocity function. So what we're saying is, we're linking these two things and saying, sure, a is a function of t, which means a instantaneous. The instantaneous value of acceleration is, by definition, the instantaneous rate of change of velocity. Well, what we are saying is that instantaneous rate of change happens to be the number 0. It is that because when this function gets to a minimum, or if it got to, this function actually would get to a maximum over here and do something like that. Here's a local maximum, but that's also a place where, look, the instantaneous rate of change, the slope of that tangent happens to be the number 0. Okay, so we have to use this fact and say, okay, here is the function v as a function of t. We need to say, okay, when it has this minimum, that means that, well, the slope of the tangent equals 0. So we need to differentiate our velocity function with respect to time, set that function equal to 0. So we need to differentiate with respect to time this velocity function. And set that equal to 0. So let's see, differentiating means the algorithm is we take this exponent, we multiply by that coefficient, we decrease the size of, we make this exponent 1 smaller, so that means that's 12t squared. This is really 2t to the first, so that becomes, well, the number 2 equals 0. So this is really saying that the acceleration as a function of time is that function. And there is some time when that function equals 0. Well, that's when 12t squared equals the number 0. Equals the number 2. Or t, that's, well, is 1/6 plus or minus, right? Plus or minus? Right, here's the minus, here's the plus. Now, a problem is going to assume that there isn't a time before 0. So our most appropriate answer here is it's the time, and forgive my use of radicals, I hope you will. That's the time. We've already figured out that this is a minimum because we are able to make a qualitative sketch of this function and see what its general characteristics are, right? And there are other ways to do that, right? What you could do is you could say, well, let me make t a little bit bigger than this. Let me make t a little bit smaller than this. Again, let me come back to that part, all right? But that is the time at which this value reaches a minimum or maximum. Now we want to find, well, what is the value of v minimum? So what we say is, let's evaluate our velocity function at time 1 over radical 6, same as radical 1/6. So that function for v is 4 times t cubed, so that means over 4 times 1 over, well, let's see, radical 6 cubed. That's clunky. Minus 2 times 1 over radical 6. And you can, you want to find a number for radical 6 and plug it in, fine. Now watch, I'll do this just because. This is 4 times 1 over 6 radical 6, right? Because radical 6, this is radical 6 times radical 6 times radical 6, and so there's 6. This is now just algebra. It's not, there's no physics involved anymore. Over, 2 over radical 6. This is, yeah, now you can at least start to put these terms together, right? So you get this 4 over 6 radical 6 minus 2. Yeah, fine. You want to keep going with fractions and whatnot, fine. But that's the answer. That's 1.5 minus, right? No, sorry, that's 2/3 minus, that's 4/6 minus 12/6. Yeah, so that's negative 8 over 6 radical 6. Yeah, sure, it's negative, right? Look, we said that the function has a negative value at that instant. So this is v minimum. And I'm not using any units, forgive me. That's not the point of this exercise. The point of this exercise is to go through the process of saying, what does it mean? How do we decode a question that says, find a minimum or maximum? This generally says find the extremes, the extrema. Figure out how big they are, and figure out if they're mins or maxes. Okay, as I started to say a minute ago, there's other ways to figure out if this is minimum or maximum. What you could do is say, well, here's the size of the function at the instant I know that it's an extreme, you could say, well, what happens when v gets a little bigger than that? What happens when v gets a little smaller than that? Sorry, when t. What happens when t gets a little bigger or a little smaller than that? Well, if you evaluate the function, what you'll get is that when t gets a little smaller than capital T, the function has a, well, has a more positive value. When t gets a little bigger than our capital T value, the function has a more positive value. So that means that's another way of saying this value must be a minimum. Okay, folks? Just to recap, the way that you decode this idea, find the instant at which the function reaches an extreme, that says find the instant at which the slope of the tangent must be the number 0, where the derivative of that function has a value of 0. Right? And then we solve for that time, but then we have to put that time back into the function itself, typically, to find the magnitude of that extreme. Okay? Thank you.